Serial ATA is a computer bus interface that connects host bus adapters to mass storage devices such as hard disk drives and optical drives. Serial ATA replaces the older AT attachment standard, offering several advantages over the older interface: reduced cable size and cost, native hot swapping, faster data transfer through higher signaling rates, and more efficient transfer through an I/O queuing protocol. SATA host adapters and devices communicate via a high-speed serial cable over two pairs of conductors. In contrast, parallel ATA used a 16-bit wired data bus with many additional support and control signals, all operating at much lower frequency. To ensure backward compatibility with legacy ATA software and applications, SATA uses the same basic ATA and ATAPI command set as legacy ATA devices. SATA has replaced parallel ATA in consumer desktop and laptop computers, and has largely replaced PATA in new embedded applications. SATA's market share in the desktop PC market was 99% in 2008. PATA remains widely used in industrial and embedded applications that use compact flash storage, even though the new CFAST standard is based on SATA. Serial ATA industry compatibility specifications originate from the Serial ATA International Organization. The SATA-IO group collaboratively creates, reviews, ratifies, and publishes the interoperability specifications, the test cases, and plug fests. As with many other industry compatibility standards, the SATA content ownership is transferred to other industry bodies, primarily the INSITS T13 Subcommittee ATA, the INSITS T10 Subcommittee, a subgroup of T10 responsible for serial-attached SCSI. The remainder of this article will try to use the terminology and specifications of SATA-IO. Features. Hot plug. The serial ATA spec includes logic for SATA device hot plugging. Devices and motherboards that meet the interoperability specification are capable of hot plugging. Advanced Host Controller Interface. Advanced Host Controller Interface is an open host controller interface published and used by Intel, which has become a de facto standard. It allows the use of advanced features of SATA such as hot plug and native command queuing. If AHCI is not enabled by the motherboard and chipset, SATA controllers typically operate in IDE emulation mode, which does not allow access to device features not supported by the ATA IDE standard. Windows device drivers that are labeled as SATA are often running in IDE emulation mode unless they explicitly state that they are AHCI mode, in RAID mode, or a mode provided by a proprietary driver and command set that allowed access to SATA's advanced features before AHCI became popular. Modern versions of Microsoft Windows, Mac OS X, FreeBSD, Linux with version 2.6.19 onward, as well as Solaris and Open Solaris, include support for AHCI, but older operating systems such as Windows XP do not. Even in those instances, a proprietary driver may have been created for a specific chipset, such as Intel's. Revisions. SATA Revision 1.0-1.5 Gbps, 150 MB per second. Revision 1.0a was released on January 7, 2003. First-generation SATA interfaces, now known as SATA 1.5 Gbps, communicate at a rate of 1.5 Gbps, and do not support native command queuing. Taking 8B/10B encoding overhead into account, they have an actual uncoded transfer rate of 1.2 Gbps. The theoretical burst throughput of SATA 1.5 Gbps is similar to that of PATA/133, but newer SATA devices offer enhancements such as NCQ, which improve performance in a multitasking environment. During the initial period after SATA 1.5 Gbps finalization, adapter and drive manufacturers used a bridge chip to convert existing PATA designs for use with the SATA interface. Bridge drives have an SATA connector, may include either or both kinds of power connectors, and, in general, perform identically to their PATA equivalents. Most lack support for some SATA-specific features such as NCQ. Native SATA products quickly eclipsed bridged products with the introduction of the second generation of SATA drives. As of April 2010, the fastest 10,000 RPMs SATA mechanical hard disk drives could transfer data at maximum rates of up to 157 MB per second, which is beyond the capabilities of the older PATA/133 specification and also exceeds a SATA 1.5 Gbps link. SATA Revision 2.0-3 Gbps, 300 MB per second, second generation SATA interfaces run with a native transfer rate of 3.0 Gbps, and taking 8B/10B encoding into account, the maximum uncoded transfer rate is 2.4 Gbps. The theoretical burst throughput of SATA 3.0 Gbps is double that of SATA Revision 1.0. All SATA data cables meeting the SATA spec are rated for 3.0 Gbps and handle current mechanical drives without any loss of sustained and burst data transfer performance. However, high-performance flash drives can exceed the SATA 3 Gbps transfer rate. This is addressed with the SATA 6 Gbps interoperability standard. SATA 3 Gbps is backward compatible with SATA 1.5 Gbps. SATA Revision 3.0-6 Gbps, 600 MB per second, Serial ATA International Organization presented the draft specification of SATA 6 Gbps physical layer in July 2008, and ratified its physical layer specification on August 18, 2008. The full 3.0 standard was released on May 27, 2009. It runs with a native transfer rate of 6.0 Gbps, and taking 8B/10B encoding into account, the maximum uncoded transfer rate is 4.8 Gbps. The theoretical burst throughput of SATA 6.0 Gbps is double that of SATA Revision 2.0. The 3.0 specification contains the following changes: 6 Gbps for scalable performance. Continued compatibility with SAS, including SAS 6 Gbps. A SAS domain may support attachment to and control of unmodified SATA devices connected directly into the SAS domain using the serial ATA tunneled protocol from the SATA Revision 3.0 Gold specification. Isochronous native command queuing streaming command to enable isochronous quality of service data transfers for streaming digital content applications. An NCQ management feature that helps optimize performance by enabling host processing and management of outstanding NCQ commands. Improved power management capabilities. A small low insertion force connector for more compact 1.8-inch storage devices. A connector designed to accommodate 7-ohm optical disk drives for thinner and lighter notebooks. Alignment with the INSIT's ATA/ATACS standard. In general, the enhancements are aimed at improving quality of service for video streaming and high-priority interrupts. In addition, the standard continues to support distances up to 1 meter. The newer speeds may require higher power consumption for supporting chips, though improved process technologies and power management techniques may mitigate this. The latest specification can use existing SATA cables and connectors, though it was reported in 2008 that some OEMs were expected to upgrade host connectors for the higher speeds. The latest standard is backward compatible with SATA 3 Gbps. SATA Revision 3.1, released in July 2011, Revision 3.1 changed these features. SATA, SATA for solid-state drives in mobile computing devices, a PCI Express mini card-like connector that is electrically SATA. Zero power optical disk drive, idle SATA optical drive draws no power. Qtrim command, improves solid-state drive performance. Required link power management, reduces overall system power demand of several SATA devices. Hardware control features, enable host identification of device capabilities. Universal Storage Module, a new standard for cable-less plug-in powered storage for consumer electronics devices. SATA Revision 3.2-16 Gbps, 1969 megabytes per second. SATA Express specification defines an interface that combines both SATA and PCI Express buses, making it possible for legacy SATA and PCI Express storage devices to coexist. See the SATA Express section for a more detailed summary. SATA M2 standard is a small form factor implementation of the SATA Express interface, with the addition of an internal USB 3.0 port. See the M2 section for a more detailed summary. MicroSSD introduces a ball grid array electrical interface for miniaturized, embedded SATA storage. USM Slim reduces thickness of universal storage module from 14.5 ohm to 9 ohm. Dev Sleep enables lower power consumption for always-on devices while in a mode such as connected standby. Hybrid information allows higher performance for solid-state hybrid drives. Cables, connectors, and ports. Connectors and cables present the most visible differences between SATA and parallel ATA drives. Unlike PATA, the same connectors are used on 3.5-inch SATA hard disks and 2.5-inch disks. Standard SATA connectors for both data and power have a conductor pitch of 1.27 ohm. Low insertion force is required to mate a SATA connector. A smaller mini SATA or mSATA connector is used by smaller devices such as 1.8 inches SATA drives, some DVD and Blu-ray drives, and mini SSDs. A special eSATA connector is specified for external devices, and an optionally implemented provision for clips to hold internal connectors firmly in place. SATA drives may be plugged into SAS controllers and communicate on the same physical cable as native SAS disks, but SATA controllers cannot handle SAS disks. Female SATA ports are for use with SATA data cables that have locks or clips to prevent accidental unplugging. Some SATA cables have right or left-angled connectors to ease connection to circuit boards. Data connector. The SATA standard defines a data cable with 7 conductors and 8 ohm wide wafer connectors on each end. SATA cables can have lengths up to 1 meter, and connect one motherboard socket to one hard drive. PATA ribbon cables, in comparison, connect one motherboard socket to 1 or 2 hard drives, carry either 40 or 80 wires, and are limited to 45 cm in length by the PATA specification. However, cables up to 90 cm are readily available. Thus, SATA connectors and cables are easier to fit in closed spaces, and reduce obstructions to air cooling. They are more susceptible to accidental unplugging and breakage than PATA, but cables can be purchased that have a locking feature, whereby a small spring holds the plug and the socket. SATA connectors may be straight, right-angled, or left-angled. Angled connectors allow lower-profile connections. Right-angled connectors lead the cable immediately away from the drive, on the circuit board side. Left-angled connectors lead the cable across the drive towards its top. One of the problems associated with the transmission of data at high speed over electrical connections is described as noise, which is due to electrical coupling between data circuits and other circuits. As a result, the data circuits can both affect other circuits, and be affected by them. Designers use a number of techniques to reduce the undesirable effects of such unintentional coupling. One such technique used in SATA links is differential signaling. This is an enhancement over PATA, which uses single-ended signaling. The use of fully shielded twin-ax conductors, with multiple ground connections, for each differential pair improves isolation between the channels and reduces the chances of lost data in difficult electrical environments. Power connectors, standard connector. SATA specifies a different power connector than the decades-old 4-pin Molex connector used on parallel ATA devices. It is a wafer-type connector, like the SATA data connector, but much wider to avoid confusion between the two. Some early SATA drives included the old 4-pin Molex power connector together with the new 15-pin connector, but most SATA drives now have only the latter. The new SATA power connector contains many more pins for several reasons. 3.3 is supplied along with the traditional 5 and 12 supplies. However, very few drives actually use it, so they may be powered from an old 4-pin Molex connector with an adapter. To reduce impedance and increase current capability, each voltage is supplied by 3 pins in parallel, though 1 pin in each group is intended for pre-charging. Each pin should be able to carry 1.5 A. 5 parallel pins provide a low impedance ground connection. 2 ground pins, and 1 pin for each supplied voltage, support hot plug pre-charging. Ground pins 4 and 12 in a hot swap cable are the longest, so they make contact first when the connectors are mated. Drive power connector pins 3, 7 and 13 are longer than the others, so they make contact next. The drive uses them to charge its internal bypass capacitors through current-limiting resistances. Finally, the remaining power pins make contact, bypassing the resistances and providing a low impedance source of each voltage. This two-step mating process avoids glitches to other loads and possible arcing or erosion of the SATA power connector contacts. Pin 11 can function for staggered spin-up, activity indication, both, or nothing. It is an open collector signal, that may be pulled down by the connector or the drive. If pulled down at the connector, the drive spins up as soon as power is applied. If left floating, the drive waits until it is spoken to. This prevents many drives from spinning up simultaneously, which might draw too much power. The pin is also pulled low by the drive to indicate drive activity. This may be used to give feedback to the user through an LED. Passive adapters are available that convert a 4-pin Molex connector to a SATA power connector, providing the 5V and 12V lines available on the Molex connector, but not 3.3V. There are also 4-pin Molex to SATA power adapters which include electronics to provide 3.3V power additionally. However, most drives do not require the 3.3V power line. Slimeline connector, SATA 2.6 was the first revision that defined the slimeline connector, intended for smaller form factors such as notebook optical drives. Pin 1 is shorter than the others. Microconnector. The microconnector originated with SATA 2.6. It is intended for 1.8-inch hard drives. There is also a micro data connector, similar in appearance to but slightly thinner than the standard data connector. The micro SATA connector is sometimes called USATA or I1/4 SATA. eSATA. Standardized in 2004, eSATA provides a variant of SATA meant for external connectivity. It uses a more robust connector, longer shielded cables, and stricter electrical standards. The protocol and logical signaling are identical to internal SATA. The differences are: minimum transmit amplitude increased, range is 500 a 600 a megavolt instead of 400 a 600 a megavolt. Minimum receive amplitude decreased, range is 240 a 600 a megavolt instead of 325 a 600 a megavolt. Maximum cable length increased to 2 meters. The eSATA cable and connector is similar to the SATA 1.0 cable and connector, with these exceptions. The eSATA connector is mechanically different to prevent unshielded internal cables from being used externally. The eSATA connector discards the L-shaped key and changes the position and size of the guides. The eSATA insertion depth is deeper, 6.6 ohm instead of 5 ohm. The contact positions are also changed. The eSATA cable has an extra shield to reduce ME to FCC and CE requirements. Internal cables do not need the extra shield to satisfy ME requirements because they are inside a shielded case. The eSATA connector uses metal springs for shield contact and mechanical retention. The eSATA connector has a design life of 5,000 matings. The ordinary SATA connector is only specified for 50. Aimed at the consumer market, eSATA enters an external storage market served also by the USB and FireWire interfaces. The SATA interface has certain advantages. Most external hard disk drive cases with FireWire or USB interfaces use either PATA or SATA drives and bridges to translate between the drive's interfaces and the enclosure's external ports. This bridging incurs some inefficiency. Some single disks can transfer 157 MB per second during real use, about 4 times the maximum transfer rate of USB 2.0 or FireWire 400 and almost twice as fast as the maximum transfer rate of FireWire 800. The S3200 FireWire 1394B spec reaches 400 MB per second, and USB 3.0 has a nominal speed of 5 Gbps. Some low-level drive features, such as SMART, may not operate through some USB or FireWire or USB plus FireWire bridges. eSATA does not suffer from these issues provided that the controller manufacturer presents eSATA drives as ATA devices, rather than as SCSI devices, as has been common with Silicon Image, Micron, and NVIDIA Force drivers for Windows Vista. In those cases SATA drives do not have low-level features accessible. The eSATA version of SATA 6G operates at 6.0 Gbps. Therefore, eSATA connections operate with negligible differences between them. Once an interface can transfer data as fast as a drive can handle them, increasing the interface speed does not improve data transfer. Most newer computers, including notebooks, laptops, have external SATA connectors, in addition to USB 2.0 and sometimes USB 3.0 ports, though relatively few have built-in FireWire ports. There are some disadvantages, however, to the eSATA interface. Devices built before the eSATA interface became popular lack external SATA connectors. For small form-factor devices disks, a PC-hosted USB or FireWire link can usually supply sufficient power to operate the device. However, eSATA connectors cannot supply power, and require a power supply for the external device. The related eSATAP connector adds power to an external SATA connection, so that an additional power supply is not needed. Desktop computers without a built-in eSATA interface can install an eSATA host bus adapter. If the motherboard supports SATA, an externally available eSATA connector can be added. Notebook computers can be upgraded with CardBus or Express Card versions of an eSATA HBA. With passive adapters, the maximum cable length is reduced to 1 meter due to the absence of compliant eSATA signal levels. eSATAP. eSATAP stands for Powered eSATA. It is also known as Power over eSATA, Power eSATA, eSATA USB Combo, or eSATA USB Hybrid Port. An eSATAP port combines the 4 pins of the USB 2.0 port, the 7 pins of the eSATA port, and optionally 2 12-volt power pins. Both SATA traffic and device power are integrated in a single cable, as is the case with USB but not eSATA. Power at 5 volts is provided through 2 USB pins. Power at 12 volts may optionally be provided. Typically desktop, but not notebook, computers provide 12-volt power, so can power devices requiring this voltage, typically 3.5 inches disc and CD/DVD drives, in addition to 5-volt devices such as 2.5 drives. Both USB and eSATA devices can be used with an eSATAP port, when plugged in with a USB or eSATA cable, respectively. An eSATA device cannot be powered via an eSATAP cable, but cables are available which make available both SATA or eSATA and power connectors from an eSATAP port. An eSATAP connector can be built into a computer with internal SATA and USB, by fitting a bracket with connections for internal SATA, USB, and power connectors and an externally accessible eSATAP port. Though eSATAP connectors have been built into several devices, manufacturers do not refer to an official standard. Pre-standard implementations, prior to the final eSATA 3-bit specification, a number of products were designed for external connection of SATA drives. Some of these use the internal SATA connector, or even connectors designed for other interface specifications, such as FireWire. These products are not eSATA compliant. The final eSATA specification features a specific connector designed for rough handling, similar to the regular SATA connector, but with reinforcements in both the male and female sides, inspired by the USB connector. eSATA resists inadvertent unplugging, and can withstand yanking or wiggling, which could break a male SATA connector. With an eSATA connector, considerably more force is needed to damage the connector and if it does break, it is likely to be the female side, on the cable itself, which is relatively easy to replace. Prior to the final eSATA 6-bit S specification, many add-on cards and some motherboards advertised eSATA 6-bit S support because they had 6-bit SATA 3.0 controllers for internal-only solutions. Those implementations are non-standard, and eSATA 6-bit S requirements were ratified in the July 18, 2011 SATA 3.1 specification. Some products might not be fully eSATA 6-bit S compliant. Mini SATA. Mini SATA, which is distinct from the microconnector, was announced by the serial ATA International Organization on September 21, 2009. Applications include netbooks, laptops and other devices that require a solid-state drive in a small footprint. The connector is similar in appearance to a PCI Express mini card interface, but is not electrically compatible. The data signals need a connection to the SATA host controller instead of the PCI Express host controller. M2. M2, formerly known as the Next Generation Form Factor, is a specification for computer expansion cards and associated connectors. It is intended to replace mSATA, which uses the PCI Express mini card physical layout. Having a smaller and more flexible physical specification, together with more advanced features, the M2 is more suitable for solid-state storage applications in general, especially when used in small devices like ultrabooks or tablets. The M2 standard is designed as a revision and improvement to the mSATA standard, allowing for larger printed circuit boards to be manufactured. While mSATA took advantage of the existing PCI Express mini card form factor and connector, M2 has been designed to maximize usage of the card space, while minimizing the footprint. Supported host controller interfaces and internally provided ports are a superset to those defined by the SATA Express interface. Essentially, the M2 standard is a small form factor implementation of the SATA Express interface, with the addition of an internal USB 3.0 port. SATA Express. SATA Express, initially standardized in the SATA 3.2 specification, is an interface that supports either SATA or PCI Express storage devices. The host connector is backwards compatible with the standard 3.5-inch SATA data connector, allowing up to 2 legacy SATA devices to be connected. At the same time, host connector provides multiple PCI Express lanes as a pure PCI Express connection to the storage device. Instead of the otherwise usual approach of doubling the native speed of the SATA interface, PCI Express was selected for achieving data transfer speeds greater than 6 Gbps. It was concluded that doubling the native SATA speed would take too much time and too many changes would be required to the SATA standard, and would result in a much greater power consumption when compared to the existing PCI Express bus. In addition to supporting legacy advanced host controller interface, SATA Express also makes it possible for NVMe Express to be used as the logical device interface for connected PCI Express storage devices. Protocol. The SATA specification defines 3 distinct protocol layers: physical, link, and transport. Physical layer. The physical layer defines SATA's electrical and physical characteristics, as well as the physical coding subsystem. Physical transmission uses differential signaling. The SATA PHY contains a transmit pair and receive pair. When the SATA link is not in use, the transmitter allows the transmit pins to float to their common mode voltage level. When the SATA link is either active or in the link initialization phase, the transmitter drives the transmit pins at the specified differential voltage. SATA physical coding uses a line encoding system known as 8B/10B encoding. This scheme serves multiple functions required to sustain a differential serial link. First, the stream contains necessary synchronization information that allows the SATA host drive to extract clocking. The 8B/10B encoded sequence embeds periodic edge transitions to allow the receiver to achieve bit alignment without the use of a separately transmitted reference clock waveform. The sequence also maintains a neutral bit stream, which allows the transmit drivers and receiver inputs to be AC coupled. Generally, the actual SATA signaling is half-duplex, meaning that it can only read or write data at any one time. Also, serial ATA uses some of the special characters defined in 8B/10B. In particular, the PHY layer uses the comma character to maintain symbol alignment. A specific 4-symbol sequence, the align primitive, is used for clock rate matching between the two devices on the link. Other special symbols communicate flow control information produced and consumed in the higher layers. Separate point-to-point AC coupled LVDS links are used for physical transmission between host and drive. The PHY layer is responsible for detecting the other SATA device on a cable, and link initialization. During the link initialization process, the PHY is responsible for locally generating special out-of-band signals by switching the transmitter between electrical idle and specific 10B characters in a defined pattern, negotiating a mutually supported signaling rate, and finally synchronizing to the far-end device's PHY layer data stream. During this time, no data is sent from the link layer. Once link initialization has completed, the link layer takes over data transmission, with the PHY providing only the 8B/10B conversion before bit transmission. Link layer: after the PHY layer has established a link, the link layer is responsible for transmission and reception of frame information structures over the SATA link. FISs are packets containing control information or payload data. Each packet contains a header and payload whose contents are dependent on the type. The link layer also manages flow control over the link. Transport layer: layer number 3 in the serial ATA specification is the transport layer. This layer has the responsibility of acting on the frames and receiving the frames in an appropriate sequence. The transport layer handles the assembly and disassembly of FIS structures, which includes, for example, extracting content from register FISs into the task file and informing the command layer. In an abstract fashion, the transport layer is responsible for creating and encoding FIS structures requested by the command layer, and removing those structures when the frames are received. When DMA data is to be transmitted and is received from the higher command layer, the transport layer appends the FIS control header to the payload, and informs the link layer to prepare for transmission. The same procedure is performed when data is received, but in reverse order. The link layer signals to the transport layer that there is incoming data available. Once the data is processed by the link layer, the transport layer inspects the FIS header and removes it before forwarding the data to the command layer. Topology: SATA uses a point-to-point architecture. The physical connection between a controller and a storage device is not shared among other controllers and storage devices. SATA defines multipliers, which allows a single SATA controller port to drive up to 15 storage devices. The multiplier performs the function of a hub. The controller and each storage device is connected to the hub. This is conceptually similar to SAS expanders. Modern PC systems have SATA controllers built into the motherboard, typically featuring 2 to 8 ports. Additional ports can be installed through add-in SATA host adapters. Backward and forward compatibility: SATA and PATA. At the device level, SATA and PATA devices remain completely incompatible, they cannot be interconnected. At the application level, SATA devices can be specified to look and act like PATA devices. Many motherboards offer a legacy mode option, which makes SATA drives appear to the OS like PATA drives on a standard controller. This eases OS installation by not requiring a specific driver to be loaded during setup but sacrifices support for some features of SATA and, in general, disables some of the board's PATA or SATA ports, since the standard PATA controller interface supports only 4 drives. The common heritage of the ATA command set has enabled the proliferation of low-cost PATA to SATA bridge chips. Bridge chips were widely used on PATA drives as well as standalone dongles. When attached to a PATA drive, a device-side dongle allows the PATA drive to function as a SATA drive. Host-side dongles allow a motherboard PATA port to function as a SATA host port. The market has produced powered enclosures for both PATA and SATA drives that interface to the PC through USB, FireWire or eSATA, with the restrictions noted above. PCI cards with a SATA connector exist that allow SATA drives to connect to legacy systems without SATA connectors. SATA 1.5-bit and SATA 3-bit. The designers of SATA aimed for backward and forward compatibility with future revisions of the SATA standard. To prevent interoperability problems that could occur when next-generation SATA drives are installed on motherboards with standard legacy SATA 1.5-bit host controllers, many manufacturers have made it easy to switch those newer drives to the previous standards mode. For example, Seagate Maxtor has added a user-accessible jumper switch, known as the Force 150, to enable the drive switch between forced 1.5-bit and 1.5's negotiated operation. Western Digital uses a jumper setting called OPT1 enabled to force 1.5-bit data transfer speed. Samsung drives can be forced to 1.5-bit mode using software that may be downloaded from the manufacturer's website. Configuring some Samsung drives in this manner requires the temporary use of a SATA2 controller while programming the drive. The Force 150 switch is also useful for attaching SATA 3-bit hard drives to SATA controllers on PCI cards, since many of these controllers run at 3-bit, even though the PCI bus cannot reach 1.5-bit speeds. This can cause data corruption in operating systems that do not specifically test for this condition and limit the disk transfer speed. SATA 3-bit and SATA 6-bit, SATA 3-bit and SATA 6-bit are compatible with each other. Most devices which are only SATA 3-bit can connect with devices that are SATA 6-bit, and vice versa. Though SATA 3-bit devices only connect with SATA 6-bit devices at the slower 3-bit speed. SATA 1.5-bit and SATA 6-bit, SATA 1.5-bit and SATA 6-bit are compatible with each other. Most devices which are only SATA 1.5-bit can connect with devices that are SATA 6-bit, and vice versa. Though SATA 1.5-bit devices only connect with SATA 6-bit devices at the slower 1.5-bit speed. Comparison to other interfaces, SATA and SCSI, parallel SCSI uses a more complex bus than SATA, usually resulting in higher manufacturing costs. SCSI buses also allow connection of several drives on one shared channel, whereas SATA allows one drive per channel, unless using a port multiplier. Serial-attached SCSI uses the same physical interconnects as SATA, and most SASHBAs also support SATA devices. SATA 3-bit theoretically offers a maximum bandwidth of 300 MB per second per device, which is only slightly lower than the rated speed for SCSI Ultra 320 with a maximum of 320 MB per second in total for all devices on a bus. SCSI drives provide greater sustained throughput than multiple SATA drives connected via a simple port multiplier because of disconnect, reconnect and aggregating performance. In general, SATA devices link compatibly to SAS enclosures and adapters, whereas SCSI devices cannot be directly connected to a SATA bus. SCSI, SAS, and fiber channel drives are more expensive than SATA, so they are used in servers and disk arrays where the better performance justifies the additional cost. Inexpensive ATA and SATA drives evolved in the home computer market, hence there is a view that they are less reliable. As those two worlds overlapped, the subject of reliability became somewhat controversial. Note that, in general, The failure rate of a disk drive is related to the quality of its heads, platters and supporting manufacturing processes, not to its interface. Use of serial ATA in the business market increased from 22% in 2006 to 28% in 2008. Comparison with other buses. USB 3.0 specification released to hardware vendors November 17, 2008. Unlike PATA, both SATA and eSATA support hot swapping by design. However, this feature requires proper support at the host, device, and operating system levels. In general, all SATA devices support hot swapping, also most SATA host adapters support this command. SCSI3 devices with SCA2 connectors are designed for hot swapping. Many server and RAID systems provide hardware support for transparent hot swapping. The designers of the SCSI standard prior to SCA2 connectors did not target hot swapping, but, in practice, most RAID implementations support hot swapping of hard disks. See also. References. External links, Serial ATA International Organization, ATA Serial ATA and the Evolution in Data Storage Technology, Muhammad A. Salem, SATA-1 Specification, as a zipped PDF. Serial ATA, High-Speed Serialized AT Attachment, Revision 1.0, January 7, 2003. Errata and engineering change notices to above SATA-1 specification, as a zip of PDFs, dispelling the confusion. SATA-2 does not mean 3-bit S, SATA-IO white paper, external SATA PDFA, 502 KIB, SATA motherboard connector pinout, serial ATA connector schematic and pinout, serial ATA server and storage use cases, how to install and troubleshoot SATA hard drives, serial ATA and the 7 deadly sins of parallel ATA, everything you need to know about serial ATA, Barracuda XT, the first SATA 6-bit SHDD, mini FAQ on SATA2, USB 3.0. Versus eSATA, is faster better? UniATA, the universal, free, open-source ATA driver with PATA SATA support, adapter or converter for a SATA drive to become a PATA drive, adapter or converter for either, a PATA drive to become a SATA drive, or a PATA port on the motherboard of a desktop computer to become an SATA port.